Preparing for a quantum computing scientist interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you explain a qubit, and how is it different from a classical bit? A classical bit is either 0 or 1, while a qubit is described by a complex state vector, typically alpha 0 plus beta 1. The amplitudes carry phase information, and their squared magnitudes give measurement probabilities. The key distinction is that superposition enables interference before measurement, which classical randomness cannot reproduce. I would also emphasize normalization. The tidal probability must equal 1. That structure is what quantum algorithms exploit. While answering, focus on state vectors, superposition, measurement collapse, normalization, and why a qubit is not simply a probabilistic classical bit before measurement. Question 2. What is entanglement, and why is it useful in quantum computing? Entanglement means the joint state of multiple qubits cannot be written as independent states of each qubit. For example, in a Bell state, measuring one qubit immediately constrains the outcome of the other, even though each individual result may look random. In computing, entanglement helps create computational structure across a register. It is central to algorithms, teleportation, certain cryptographic protocols, and stabilizer-based error correction. Make sure to cover non-separable joint states, correlations stronger than classical descriptions, Bell state intuition, and how entanglement supports algorithms, communication, and error correction. Question 3. How do single-qubit and two-qubit gates work in the circuit model? Quantum gates are unitary transformations applied to qubit states. Single-qubit gates rotate the state on the block sphere. For example, X flips the computational basis state, H creates superposition, and phase rotations change relative phase. Two-qubit gates, such as C0 or CZ, condition one qubit's evolution on another. That conditional interaction is important because single-qubit gates alone cannot create entanglement. So universal computation needs both local rotations and entangling gates. In your answer, talk about unitary operations, rotations on the block sphere, common gates like X, H, RZ, C0, and why two-qubit gates enable entanglement. Question 4. What causes decoherence, and how would you reduce its impact in an experiment? Decoherence happens when a quantum system leaks information into its environment, degrading phase coherence or relaxing population. I usually separate it into T1 energy relaxation and T2 dephasing. Experimentally, I would reduce it by improving isolation, filtering control lines, lowering thermal noise, shortening gate durations, and using dynamical decoupling where appropriate. At the circuit level, I would also minimize depth and apply mitigation methods because decoherence compounds quickly in NISQ devices. Be sure to mention system environment coupling, T1 relaxation, T2 dephasing, gate time versus coherence time, shielding, calibration, dynamical decoupling, and error mitigation. Question 5. Can you explain quantum error correction at a high level? Quantum error correction protects information by encoding one logical qubit into an entangled state of many physical qubits. Because we cannot clone an unknown quantum state, we do not directly measure the logical state. Instead, we measure syndromes, which reveal what type of error likely occurred without collapsing the encoded information. Stabilizer codes such as the surface code are prominent because they use local checks and have practical thresholds. The trade-off is significant physical qubit overhead. While answering, focus on encoding logical qubits into many physical qubits, syndrome measurements, stabilizers, no cloning constraints, thresholds, and the difference between detection and correction. Question 6. What is the difference between gate fidelity, readout fidelity, and coherence time? Gate fidelity measures how close an implemented quantum gate is to the ideal unitary operation. Readout fidelity measures how accurately the final qubit state is classified during measurement. Coherence time, such as T1 or T2, describes how long the physical qubit preserves quantum information before relaxation or dephasing. All three matter differently. High gate fidelity supports deep circuits, high readout fidelity improves statistics, and long coherence time provides the operating window for computation. Make sure to distinguish operation accuracy, measurement accuracy, and intrinsic lifetime metrics, then connect them to circuit depth, benchmarking, hardware quality, and algorithm feasibility. Question 7. How would you characterize noise on a quantum device? I would start by separating state preparation and measurement errors from gate and idle errors. For scalable characterization, randomized benchmarking is useful because it estimates average gate error without full process tomography. If I needed deeper diagnostics, I might use interleaved benchmarking, cycle benchmarking, Ramsey experiments, or crosstalk measurements. Full tomography is informative but scales poorly. The practical goal is not just estimating noise, but identifying whether calibration, pulse shaping, or compilation can improve performance. In your answer, talk about randomized benchmarking, process tomography, measurement calibration, crosstalk analysis, spam errors, and why scalable diagnostics often beat full tomography. Question 8. How does Grover's algorithm achieve a quadratic speedup? Grover's algorithm speeds up unstructured search by amplifying the probability amplitude of marked solutions. The oracle flips the phase of the target state, and the diffusion operator reflects amplitudes around their average. Repeating this sequence rotates the state vector toward the solution's subspace. Classically, finding one marked item among n possibilities takes order n queries, while Grover needs order square root n. It is powerful, but the advantage is quadratic, not exponential. Be sure to cover unstructured search, oracle marking, amplitude amplification, inversion about the mean, square root complexity, and why the speedup is quadratic rather than exponential. Question 9. What makes Shor's algorithm important, and what are its practical limitations today? Shor's algorithm is important because it factors large integers in polynomial time, threatening RSA-style cryptography if run on a sufficiently large fault-tolerant quantum computer. The core quantum step is period finding, supported by the quantum Fourier transform. Today, the limitation is not the mathematics but the hardware. Meaningful factoring requires many logical qubits, extremely low logical error rates, and long coherent circuits. Current NISQ machines are far from that regime. While answering, focus on factoring, period finding, quantum Fourier transform, cryptographic implications, fault-tolerant resource requirements, and why current noisy hardware cannot run meaningful scale Shor. Question 10. How would you approach designing a VQE experiment for a small molecule? I would begin by mapping the molecular Hamiltonian to qubits, using Jordan-Wigner or Bravyi-Kitaev, depending on structure and resources. Then I would choose an ansatz, such as UCSD for chemistry motivation, or a hardware-efficient ansatz for near-term execution. The objective is the measured energy expectation, optimized by a classical routine. I would group commuting poly terms to reduce measurements, monitor shot noise, and benchmark small cases against exact diagonalization. Make sure to cover Hamiltonian mapping, ansatz choice, parameter optimization, measurement grouping, shot noise, hardware constraints, and validating against classical exact diagonalization. Question 11. What are barren plateaus, and how can they affect variational quantum algorithms? Barren plateaus are regions of the optimization landscape where gradients become exponentially small, making parameter training extremely difficult. They often arise in deep, highly expressive, randomly initialized variational circuits. In practice, an optimizer may appear stuck even with many evaluations. To mitigate this, I would use problem-inspired ansatz structures, shallow circuits, careful initialization, local cost functions, and possibly layer-wise training. The main lesson is that expressibility alone is not enough. Trainability matters. In your answer, talk about exponentially vanishing gradients, random deep ansatz circuits, trainability problems, initialization, problem-inspired ansatz design, locality, and layer-wise training. Question 12. How do you decide whether a quantum algorithm is suitable for NISQ hardware? I would evaluate whether the algorithm fits the device's physical constraints before discussing advantage. That means checking qubit count, circuit depth, two-qubit gate requirements, connectivity, coherence limits, and measurement overhead. I would also compare against strong classical baselines, not weak ones. Many NISQ demonstrations are scientifically useful, but not commercially advantageous. A suitable NISQ algorithm should tolerate noise, use shallow circuits, and solve an instance large enough to teach something beyond simulation. Be sure to mention circuit depth, qubit count, connectivity, noise tolerance, measurement overhead, classical baseline comparison, problem size, and whether the claimed advantage is realistic. Question 13. What happens during quantum circuit transpilation, and why does it matter? Transpilation converts an abstract quantum circuit into instructions executable on a specific device. First, gates are decomposed into the hardware's native gate set. Then, logical qubits are mapped onto physical qubits, subject to connectivity constraints. If two qubits need to interact but are not connected, the compiler inserts swaps, increasing depth and noise exposure. Good transpilation matters because two circuits that are mathematically equivalent can have very different experimental performance on real hardware. While answering, focus on mapping logical qubits to hardware qubits, native gate decomposition, connectivity constraints, swap insertion, depth optimization, and noise-aware compilation. Question 14. How would you interpret a quantum measurement result with finite shots? A finite shot measurement gives samples from a probability distribution, not exact probabilities. If I run 1,000 shots and observe a bit string 520 times, I would treat that as an estimate with statistical uncertainty, not a precise value. For expectation values, I would compute averages and attach confidence intervals where possible. I would also consider readout calibration and mitigation. Small differences between outcomes may be noise, unless they exceed expected sampling and device errors. Make sure to cover sampling distributions, shot noise, confidence intervals, expectation value estimation, readout error correction, and avoiding overinterpretation of small probability differences. Question 15. Tell me about a recent quantum computing paper you found interesting and how you would evaluate it critically. I would summarize the paper's core claim first, what problem it addresses, what method it introduces, and what result improves on prior work. Then I would test the claim against assumptions, baselines, resource estimates, and scalability. For an experimental paper, I would look closely at calibration, error bars, device noise, and reproducibility. If I were evaluating it in a lab, I would reproduce the smallest meaningful benchmark before trusting the broader conclusion. In your answer, talk about summarizing the contribution, checking assumptions, comparing baselines, reviewing experimental evidence, assessing scalability, and identifying what you would reproduce first. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.